Dear classmates, welcome to the VLSI testing class. Today we are going to introduce a very useful modern topic, test compression. Here is our course roadmap. With the foundation of DFT and the built-in self-test, we can now introduce the test compression topic. Here is our motivating problem. Suppose that you work very hard and generate a lot of test patterns. The total volume of test data is 100 gigabits. Unfortunately, your ATE has only 80 gigabits. So your manager asks you to reduce 25% of your test patterns. But you are required to maintain the same fog coverage. What can you do? Suppose that in this table, each row shows a test pattern and each column shows a fault. For example, test pattern T1 detects fault 2. From this table, we can easily see that we just remove test pattern T1. We can reduce 25% of test patterns because T1 does not detect any additional fault. So this concept is test compression. So why am I learning this chapter? Test compression reduce test data so that we can reduce ATE costs, test costs, and also some package costs. Test compression is an essential topic for modern complex designs. Here is a famous quotation, Occam's razor principle. It says that the simplest answer is the best. This is a very suitable quotation for test compression. In the test compression chapter, we will first give an introduction. Then we will introduce software test compression techniques. We have dynamic test compression and static test compression. After that, we will introduce hardware topics. We can divide them into test stimulus compression and the test response compression. At the end, we will show some industry practice and conclude this chapter. What is test compression? Test compression reduces the amount of test data, and hopefully we wish to keep the same test quality. So why do we need test compression? Number one reason is, of course, to reduce the amount of test data, so that we can reduce ATE costs. With test compression, we can also reduce test time, so we can reduce test application costs. And finally, with test compression, we can reduce the number of DFT pins, such as scan-in and scan-output pins, so that we can reduce package costs and ATE costs. So what is the reason that we can compress test data? From the input test stimulus side, we know that ATPG patterns typically have many don't care bits. This is why we can compress the input test stimulus. On the output side, for test responses, we know that not every bit in the test response needs to be observed. This is the reason why we can compact the test responses. Here is a small notice about the word compression and the compaction. If you read our outline carefully, you can see that we use different words. For input test stimulus compression, we use the word compression because it is lossless. We cannot change any bit during the compression process. However, on the output side, we use test response compaction. We use the word compaction because it can be lossy. We do not have to reconstruct the test response. We only need to detect the fault. But you don't have to be worried about this. Some people just use them interchangeably. This picture shows that the amount of test data volume is increasing very rapidly. On the x-axis, we show the number of gate count in million gates. On the y-axis, we show the volume of test data in gigabits. From this figure, we can see that the amount of test data is increasing very rapidly. Suppose that we have an ATE system that has 500 pins. Each pin has 64 megabits of memory. Then totally, this ATE available memory is 32 gigabits. Suppose that in our design we have 1 million flip-flop and we generated 60,000 test patterns. So the total amount of scan data is 60 gigabit, which is larger than the ATE memory. In this case, we will need to perform test compression. Otherwise, we cannot fit our test pattern into the ATE. This slide shows the ITRS International Technology Roadmap for Semiconductor prediction in the year of 2013. On these three rows, they show the predicted test compression ratio, which is defined by the amount of original test data over the amount of compressed data. We can see that the predicted test compression ratio is increasing over the years. By the year 2020, it was predicted that more than 1,000 times of test compression would be needed. This is a very large compression ratio. Historically speaking, test compression was performed very early in the research history. As early as 1980s, people started to look at software test compression techniques. At that time, compression was performed inside the ATPG. There was no extra DFT hardware inserted. The purpose is to reduce the number of test patterns. In 1990s, hardware test compression techniques began to appear. People focused on test stimulus compression at that time. The purpose is to reduce the number of scan-in or scan-output pins. Also, we want to reduce the amount of test data. In the year of 2000, people began to look at test response compaction. The reason was that there were many unknown outputs. If we cannot handle these unknown outputs properly, they would corrupt our test response compaction. After 2010, when test stimulus and test response compression were pretty much done, people start to look at test point insertion to reduce the number of test patterns. Now let's start from software techniques. There are dynamic test compression, and static test compression. In this video, we first introduce DTC technique. Static test compression will be introduced in the next video. This slide compares the concept of static test compression (STC) and the dynamic test compression (DTC). In a typical ATPG flow, we first select a target fault, and then we try to generate test patterns for this target fault. After we are done, we would try to compact more target faults into the same test pattern. If this is doable, we would select the next target fault. We continue in this loop until it is not possible to compress more target fault in the current test pattern. At that time, we will leave this loop and perform X-filling. X-filling fills all the don't care bits in the pattern, and we perform a fault simulation. If the fault coverage is not good enough, we will go back to select the next target fault. If the fault coverage is good enough, we will leave the loop and perform static test compression, and then we are done. During this process, we can see that dynamic test compression is performed during the test pattern generation process. It requires more CPU time, but it is more effective than static test compression. On the other hand, static test compression is performed after the test patterns are generated. It requires less CPU time, but the effectiveness of STC is worse than dynamic test compression. In summary, test compression technique increase the CPU time, but hopefully we can reduce the test application time, so this investment is worthwhile. We will introduce a simple dynamic test compression technique called Foden X, proposed by Gould in the year of 1981. Foden X algorithm is based on the Foden algorithm with some small modification. In step 1, we select a primary fault, F1, and we generate a test cube, T1. If we fail, we remove fault F1 from the fault list. We don't need to try this fault again later. In step 2, if test generation for F1 is successful, then we backtrace from the output with an unknown value, and then we select one undetected fault from the backtrace column of the output. Suppose we select F2. We call this a secondary fault. And then we generate a test cube based on the existing test pattern T1. If we fail, we can continue to try the next secondary fault, F3, but we still keep F2 in the fault list. This fault can be tried again later. We repeat step 2 until 3 conditions are satisfied. It can be either timeout condition or we have many continuous failure, or there is no more output with unknown values. Here we show a Foden X example. Suppose that we first choose a primary fault, which is G1 output stuck at 0 fault. we would do a PODEM test generation for this 4. First, we backtrace to input B and assign it to 1. And we backtrace to A and we assign A to 1. Then we would like to propagate this through gate G3. So our objective is G2 output equal to 0. We backtrace to C and we assign C to 1. Again, we backtrace to E and we assign E to 1. Then, suppose that we decide to propagate through G5. So, we assign H to 1 and we achieve our objective. The test cube so far is 11111 XX. So far, this is exactly the same as the original PODEM algorithm. After that, we will backtrace from the output with an unknown output. In this example, the lower output has the value X. So we will backtrace from this output to the input. Along the backtrace path, we find that K stuck at 1,4 is still an undetected fault. So we decide to choose K stuck at 1,4 as the secondary fault. So now our target fault is K stuck at 1,4. Our objective is to assign K to 0. After the simulation, D prime reached the primary output, so the fault is detected. Now the test cube is 11111 X0. Because all the output has been specified, so the dynamic test compression ends here. Now it's time for you to do an exercise. Suppose we want to reduce our previous dynamic test compression. Given the same primary fault, G1 output stuck at 0,4. But this time, suppose that we choose to propagate through G6 to the output. Then, please choose the secondary fault, H stuck at 0,4. Now please pause the video and work on this problem. Are you ready for the answer? Now let's look at the answer. For the primary fault, suppose that we already generate a test cube 1111 XX1. Now we move on to the secondary fault. Our objective is H equal to 1. So we assign H to 1, we run the simulation, and we generate a D. If we want to propagate through G4, then we assign J to 0. And after the simulation, the value D reaches the primary output. So we generate a test 111101. This is a fully specified test pattern because all the bits have been specified. In summary, in this video, we have introduced the concept of test compression. Test compression reduces test data. It also reduces the test application time and also ATE costs and the number of DFT pins. In this video, we also introduce software test compression techniques, the Potent X algorithm. The Potent X algorithm belongs to the dynamic test compression category. DTC is performed during test pattern generation. It is relatively slow, but more effective. On the other hand, static test compression (STC) is performed after test pattern generation. It is potentially faster, but less effective than dynamic test compression. This is the end of this video. Thank you for watching.